So I was kind of bold when I put robust, because I'm really only going to show one example that we've fully characterized, but I'm going to kind of take you on this journey of what we've been doing when working with these selenium cap surfaces that I think is potential to open up ways to generate well-defined catalysts in a broader context. So just to kind of put everything what we do in my group onto one slide, we've seen a couple introductions for surface organometallic chemistry. We're definitely within that regime. What we do is we tailor a material interface to interact with some sort of organometallic precursor that we kind of go in knowing that a precursor should promote a certain reaction. And then we go ahead and mix these together, spend a lot of time characterizing what these well-defined organometallics are, and then apply them to some catalytic reaction. So the advantage of this method is the potential to optimize the structure and function of your catalytic site to promote this, to move this particular part of heterogeneous catalysis in a way that is more predictable. Okay? So truth be told, the functional groups on these surfaces are generally pretty limited. So for the focus of this talk, the FG here is always going to be some sort of hydroxyl group. Okay? And really what we spend a lot of time in is trying to figure out what this dashed line means. What is dictating this interaction and how can we control it? Okay? Because coming from a hardcore organometallic background and putting this in the context of heterogeneous catalysis, really the largest application of organometallic heterogeneous catalysis is for the reaction of olefins to make polyolefins. Okay? And so these are sort of the three main catalysts that are used industrially for the synthesis of polypropylene or polyethylene. So you have the classic Ziegler type systems that are really used for polypropylene and to some extent broad molecular weight distributions of polypropylene or polyethylene. The Phillips catalyst, which is used for the synthesis of high density polyethylene. And this holy trinity, so that's from John Severn's book, Tailor-Made Polymers. So the holy trinity, if you're into French cooking, is onions, carrots, and celery. And if you're into olefin polymerization, your holy trinity is MAO or alkyl aluminum, an oxide, and a metallocene. Okay? So these three systems are available industrially. We've spent a lot of time looking at how one of these particular holy trinity systems operates. So this is in collaboration with Chevron Phillips. So this is sort of our Manhattan or our New York subway map for all of the things that go on in this particular mixture. So this is a mixture of triisobutyl aluminum, this monobutylated zirconocene dichloride, and aluminum oxide. What you need to happen is that the triisobutyl aluminum activates the metallocene dichloride to form a mixture of zirconium hydrides, only one of which is active in the polymerization reaction. And you need an excess of dativa because you need to carry out this reaction, but you also have to scavenge all of the OH groups on the alumina surface to prevent undesirable reactions between aluminum OHs and the generated hydrides in situ. Having all of these things happen at the same time, eventually some of this hydride finds the functionalized aluminum oxide, and you make this ion pair that we were able to characterize. Okay? You'll notice this is a cationic ion pair. This is the first time somebody's seen something like this on one of these heterogeneous catalysts. And it shows that ion pairs are really important because you need those to make polyethylene. That's something that had been appreciated by the organometallic community for quite some time. But it also shows that even though in this complex network of reactions, if they're set up right, of course the industrial people have known how to do this for a long time. If they're set up right, you can get just precisely what you need to have it, even though other things form. And even though that there are potential for a lot of side reactions, you have this really unique self-assembly which gives you just enough zirconium on the surface to generate your catalyst. Okay? So ion pairing is really important if we think about it in the context of olefin polymerization catalysis. But something that's buried in this study is that, as I mentioned, if you just take alumina, that's decorated with OH groups. You take alumina, react it with a zirconium hydride, you generate something that's completely inactive. Okay? So in this case, you have a situation where the support is turning off the catalysis. Okay? You add TIBA in the presence of the metallocene dichloride to generate your ion pair. The TIBA is scavenging the surface OH groups. You have some leucites, a very small quantity of leucites present on the alumina surface that's allowable to form this ion pair through this hydride abstraction reaction. So we basically have two extremes built into this network that are shown here. Okay? If you don't have everything mixed right, you can't generate your ion pair. If you can't generate your ion pair. If you do have everything in the proper mixture, you do generate your ion pair. So that's a very empirically designed catalytic system for these alkyl aluminums, oxides, and metallocenes. And really what we're coming in is how can we predict if a surface is going to form an ion pair or not? Okay. And so here's the 4 essential reactions in surface organometallic chemistry. So if you take some sort of ligated organometallic and react it with an oxide, this is the most typical reaction pathway. You do proteolysis. So if you're thinking about this in terms of generating an ion pair, we have a direct analogy in solution chemistry. That's just hitting an organometallic with a strong acid, so some sort of acid with a weakly coordinating anion. We have the abstraction reaction, which is essential to generate the ion pairs in that industrial heterogeneous catalyst. And we have an analogy here as well. If we take a strong Lewis acid plus an organometallic again to make an ion pair. Okay. What's missing is the ability to activate a metal chloride. Okay, so I started off as an organic chemist that was interested in reaction methodology. So if you want to make a cation and you're an organic chemist, you reach for silver triflate or silver PM6. And what that does is that it extracts a metal chloride and you make an ion pair. Okay? There's a variety of weakly coordinating anions that we have at our disposal nowadays. So these are sort of the first generation weakly coordinating anions that were discovered in the superacid literature. This is a tetra-alkoxyaluminate developed by Ingo Grossing. This is a carborane anion because for those of you in the chemistry community, if you're in Southern California, you're inundated with carboranes. So we have a variety of ways to do these halide abstraction reactions in solution, but we really don't have any ability to do this when we go over to the functionalized oxide surfaces. So that's where we kind of started and approached this. And if we think about the weakly coordinating anions shown here, they have properties that we're able to predict. So these weakly coordinating anions, the conjugate acids are strong acids. Okay, so what I'm showing here is gas phase acidity. Doing that on purpose because gas phase acidity is something that we can use to think about acidity on surfaces as well. If you form contact ion pairs with trioctyl ammonium salts, you can measure the new NH stretches, and you can see that as the acid becomes stronger, the new NH shifts to the blue because that's indicating a weaker contact ion pair solution. That was worked by Chris Reed at UCR. And there's another one, which is the silicon NMR chemical shift. Okay, so as you see, when you start from weaker acids that form strong contact ion pairs, you have a shielded NMR chemical shift. And as you go to the more weakly coordinating anions that are stronger acids that form weaker contact ion pairs, you have something that has a very de-shielded silicon NMR chemical shift. Okay, so really acidity, weakly coordinating anions, silicon NMR chemical shifts, all 3 of these things are related. Okay. So we got into this with the perspective of going for sulfated oxides. Why did we choose sulfated oxides? So we saw this in the morning session. The sulfated oxides are a very complicated material. I'm really overly simplifying what these Bronsted acidic sites will probably look like. This is actually work from Joachim Sauer's group using DMT periodic models, where the sulfate is bound in a tripolar fashion to the zirconium oxide surface, and the proton lays near the sulfate. Okay? As Zola showed earlier today, this is a drastic oversimplification. There's a variety of other polysulfate sites that are on this material as well. So why did we approach this in the context of this problem here when thinking about weakly coordinating anions? It's because when I was -2 years old, Arata and Hokkaido had generated this material, contacted it with very weak Hammett bases, and estimated the acidity of the Bronsted sites on sulfated oxides to be 4 orders of magnitude more acidic than sulfuric acid. So this should be a weakly coordinating anion. Okay? I'll point out I'll show you in a moment, this acidity measure is wrong. Okay, this is not a superacid by any stretch. Okay, and that was first hinted at by Drago in the 90s, who was doing TPO measurement showing this is not a superacid. But this material, these sulfate sites do act like weakly coordinating anions. So if you react them with this zirconocene dimethyl, you liberate methane, generate this metallocenium fragment that Tobin Marks and Max Telfero have been working on for quite some time. And this is very active in olefin polymerization. So we have something that appears to have strong acidity and acts as a weakly coordinating anion. Okay. So I mentioned that the Bronsted sites on the sulfated oxide are absolutely not superacids. This was some work that we did a few years ago, where we were essentially titrating the acidity of these sites by adding these dialkyl aryl-phosphines. Now, I'm not saying that we have a pK, you can't really apply pK to solid acidity, but what we have here is we have phosphines that form well-defined phosphoniums. All of the phosphines shown on this slide form well-defined phosphoniums from solid-state NMR studies. And what we see is that they bind to the surface following typical linear type binding isotherms. As the acidity of the phosphonium drops, the association constant drops, which is exactly how you expect weak acids to react with weak base. Okay. But then we had a second set of results that showed if we take this allyl triisopropylsilane and react with sulfated zirconia, and then take a silicon solid-state NMR, we immediately saw something that jumped out to us because our major species in the silicon solid-state NMR is at 53 ppm. Okay? 53 ppm means that we probably have a Lewis acidic silicon. Okay? How do we know it's a Lewis acid? Well, we can absorb a Lewis base, such as triethylphosphine oxide, in solution chemistry. This is the Gutman-Beckett method. Russ Drago had been developing this heterogeneous Gutman-Beckett method in the 90s. So this is a sililium generated in solution, triethyl sililium, coordinated to TPO. We have a change in the phosphorus NMR chemical shift from free TPO when it forms the anodes. So we see that we have delta-delta, in this case, of 42 ppm. We add TPO to this material, we get 2 peaks, which is not surprising because you can see we have multiple species in the silicon NMR. And in those 2 peaks, the major peak shifts with the delta-delta of 43, telling us that we have something that has sililium-like character. So if you look in the sililium ion literature, what sililium ions do is they activate CF bonds. So indeed, if we take trifluorotoluene in the presence of silane at 80 degrees, we do turn over to make the dehydrofluorinated product. There's modest activity. If you compare it to the state-of-the-art weakly coordinating anions, so these are typically carbureting anions that were looked at by Chris Reed and Oleg Ozerov, and lately by Hosea Nelson, you have much higher activities in hydrodefluorination. This was the most active heterogeneous species for hydrodefluorination chemistry. So we know that we have something that really is behaving like a sililium ion. Okay. So what's going on with respect to this sort of divergence in behavior of being a non-superacid and a weakly coordinating anion? So this is something that's really been talked about quite a bit through this community from the Hall group, some work by Davis, Del Ferro, and Marks and Lerner, where they had all suggested that the proton's probably over on a ZR-ZR bridge. Okay? So you never really make anything that would look like a superacid because zirconium oxide's a weak base. So if you mix a weak base and a strong acid, you shouldn't get a superacid. So the proton's going on the ZR-ZR bridge, and then in the silicon case, or in the organometallic case, you go on to the sulfate. And that's consistent with these small cluster DFT models that we have, which contain a triphotyl sulfate, this small zirconium oxide cluster, and these have NMR chemical shifts that are closer to what we see experimentally, compared to putting the silicon on a ZR-ZR bridge. Okay. So here's the sort of relationship that we have so far. If you have a free sililium ion, you're somewhere over here on the wall in terms of our NMR scale. That's because you're coupling the HOMO, which is a silicon carbon bond, to the LUMO in the paramagnetic rotation models that are out there for NMR. So this is a very de-shielded NMR chemical shift. You approach a weakly coordinating anion, you parameterize silicon, you push the signal up the field. Okay? So these are a variety of small molecule sililiums, triisopropylsilane, and TIPS triplet showing that behavior. This is where sulfated zirconia lies on our scale. These are the other oxides that have been reported, and this is that other peak, which is showing that we just touched some OH groups on the sulfated oxide. So we have this linear relationship, or modestly linear relationship between the experimental silicon NMR chemical shift and the deprotonation energy. And as chemists, we're never really satisfied when we have a good result. So we have something, we understand the weakly coordinating behavior, but what we want is something more weakly coordinating. So what we did is we borrowed an idea from the zeolite community that has been working with strong Bronsted sites. which are generally thought to be some sort of Lewis acidic aluminum interacting with the silane. Okay? Now, I'm not going to get into the arguments about what these are in the heterogeneous community. I'm thinking about this like an inorganic chemist. What this is a Lewis acid coordinating to a silane. So can we make some sort of designer weakly coordinating anion on support? And this is something that had been done by John Holzer using our typical tris pentafluorophenylboranes and Jean-Marie Basselet. So what we had done is taken this very strong aluminum Lewis acid by angle crossing. We made this weakly coordinating, this very strong Bronsted acid. I'm going to skip the characterization. What we have here is something that is very Bronsted acidic from a gas phase acidity perspective. This is a DFT model that matches all of our experimental results. When we graft a silane on it, we shift downfield by another 13 ppm, indicating to us that this is a more weakly coordinated support. Okay. So I mentioned in the title that this was all going to be about silurium abstraction, but what I've been telling you is how we generate the siluriums for the most part. And what we've been doing lately is exploiting the very strong Lewis acidity of these silurium ions so we can activate organometallics and sort of break out of this standard grafting reaction that's very common in surface organometallic chemistry. And that has some practical ramifications because in some cases, for example, this organopalladium catalyst for olefin polymerization, we can graft this cleanly, we can characterize this very well, but we only have 9% of the palladium intact. Okay. So we looked at this from the perspective of, well, the problem here is that we're starting from a dimethyl palladium, and we want to do the halide abstraction, which is more common in the chemistry of palladium heterogeneous catalysts. So that's what we did. We took this organopalladium methyl chloride, reacted with this weakly coordinating silurium ion pair. We see TIPS chloride, and we generate this ion. The elemental analysis shows that we have roughly 1 palladium per silyl chloride that comes off. This is some characterization data in collaboration with the Ames NMR lab. This is a proton-fluorine NMR correlation. And what we're able to do here is fit the proton-fluorine dipolar coupling between the aluminum anion and the protons on the organopalladium. This is a picture of this actual weakly coordinating anion pair. I told you before, using the protonylysis method, we only have 9% of the palladium sites that are active. If we install a C13 label here and then react with vinyl chloride, we generate essentially 100% of C13 labeled propylene. In this reaction, this is the NMR spectrum showing the C13 label built into the propylene molecule. The way this works is through the work that my PhD advisor actually did. We coordinate vinyl chloride to a 2-1 insertion, chain walk, and beta chloride eliminate to make the C13 labeled propylene product. So we went from 9% to 100%. We generate very high molecular weight polymeric products. This is if you take this catalyst activated with a halide abstraction reagent in solution, you generate this sort of globular massive polymer. If you take the heterogeneous material, you generate these really nice pellets, and you can see that from the SEM images that we're generating pellets with the heterogeneous and just a mass for the homogeneous catalyst. And to my knowledge, this catalyst produces the highest molecular weight copolymer when we do a copolymerization of methyl acrylate and ethylene. So Paul showed us that palladium is the most expensive transition metal on the periodic table, so we took the most expensive metal on the periodic table and made carbon films. So this is emerging to be a very robust methodology to make well-defined sites on surfaces. So we have silurium capped sulfated zirconia and silurium capped, we refer to this as ASO for aluminum silicon oxide. We have not met a metal halide we cannot abstract with this methodology. This is just showing a couple halides that we're able to abstract, but we have not met one we can't do yet. We can abstract iridium chloride from correlation chemistry. We can make phosphinium ions and sulfated zirconia and gold cations. And don't tell Dick, but we can do ruthenium metathesis catalysts and generate ruthenium metathesis catalysts in one step that have very high turnovers of one density metathesis. So with that, I'd like to thank the people that did the work. This is a picture of my group as of a few days ago. A lot of the work was done by Jessica and Damien. So these are my first generation students. Zhao Xin did a lot of the work on the halide abstraction of palladium. Thank them for the money. your time and listening, and I'd be happy to take any questions.
Thank you very much. Questions? I have a kind of a history question when you were -2. What is the reason that they measured it to be a superacid?
Oh, yeah.
I've heard about this a lot. I'm curious, what actually turned out to be the case?
So this was sort of the evidence, right? They took a variety of Hammond indicators and they soaked the solid material in the Hammond indicators and they just looked to see if it changed color. So these colorimetric probes for acidity have been kind of washed out of the community because they're just not, first, they're not characterized. There was no characterization that they accepted a proton. It was just literally turned yellow.
Okay.
And plus that they try to apply solution acidity methodologies to solid acids, and that's just flawed permanently. So it turns out this compound absorbs on a sulfated oxide and probably makes a charge transfer complex, which is why it turns yellow.
Gotcha. Okay, thank you.
Yeah.
Any other questions? All right, if not, let's thank our speaker and host again.